Advanced Algebra 2, Concept 13, Classifying and Evaluating Polynomials. So let's just start with the definition. A polynomial function is a monomial, that means a single term, or it can be a sum of monomials. And remember, a difference can be expressed as adding a negative. There are two criteria for an equation in math to be a polynomial function. The first criteria is that the coefficients are all whole numbers. And remember that whole numbers are 0 and counting numbers, like 1, 2, 3, 4. And then the second criteria is that the coefficients are all real numbers. So those are the multiplying term numbers in front of our exponent terms. And then two other criteria is that the largest, not criteria, just characteristics of a polynomial. The largest exponent in a polynomial is its degree. And then it's written in standard form if the terms are written in descending order of exponents. So look at the table below. You'll need to know this information about classifying polynomials. So let's start with the polynomial that is degree 0. Its type is a constant, and when you look at the equation, you'll understand that because you'll just see a number there, like f of x equals negative 14. Technically, the variable term is to the 0 power, so that's why it's degree 0. Now, a degree 1 polynomial is linear, and its input is to the first power. A degree 2 polynomial is quadratic, and its largest exponent is the second power. Degree 3, its type is a cubic, and its largest exponent is the third power. Degree 4 is a quartic, its largest exponent is 4, and then finally degree 5 is a quintic, and its largest exponent is 5. We don't use quintic a lot, but it's just good for you to know that type of polynomial. All right, in example 1, let's decide whether the function is a polynomial. So we're thinking about our two criteria, and if we have whole number exponents, first of all. So 3, 1, and 0, yes. And then real number coefficients, which we do, so this is a polynomial. Now I'm checking to see if it's in standard form, and it is, because our exponents start with 3 and then work their way down, 1 and then 0. So its degree is 3, and its type then is a cubic. Our leading coefficient, so that's the multiplier of the largest exponent term, which is negative 2. And I just abbreviate that to LC for leading coefficient. Now let's look at B. So first let's examine our exponents. Let's see if we have whole numbers, 3, 4, and 0. And if we have real number coefficients, which we do, they're kind of strange, but they are all real numbers. So yes, this is a polynomial. But it's not in standard form, so we need to rearrange it. We need to put our x to the fourth term first, then our x to the third, and then our constant. So its degree is 4, and it's a quartic. And then the leading coefficient is square root of 2. Now, C, let's start again with those exponents. Right away, we see negative 1. Negative 1 is not a whole number, so this is not a polynomial, and we just are not going to work with it in this unit. It's an equation, just not a polynomial. Now, D, let's do the same thing. Let's examine those exponents. The exponent of x, that's a legitimate thing to do, but it's not a polynomial because it's not a whole number. All right, now let's evaluate. So we can evaluate polynomials, which means find out what their value is when you put in certain values for their input. And we're going to find out what f of x is when we plug in 2. So we're going to, this is called direct substitution. So f of 2 equals negative 3 times 2 cubed plus 2 squared minus 12 times 2 minus 5. So with each of these terms, I do my exponents first, then I'm going to multiply, and then I'm going to add and subtract left to right. So negative 24 plus 4 is negative 20, minus 24 is negative 44, minus 5 more is negative 49. So I can write that as f of 2 equals negative 49. And my function notation is really convenient because it gives me a record of what I plugged in. So when I plug in 2, my output is negative 49. Now I'm going to show you a different method for evaluating a polynomial. This is a method called synthetic substitution, and it's just using a pattern found with the coefficients. So this was discovered by mathematicians who came before us. So the first thing you do is you write the coefficients of your function in order of descending exponents. If you're missing an exponent, we will put in a 0 placeholder. So 2 is our x to the 4th, negative 5. We are missing an x squared term, so we will put in 0 for that, then negative 4 and 8. You space them out, and then you do an elongated L. Out to the side, you're going to put the value that you're plugging in, which is 3. So now step 2, you're going to bring down your leading coefficient, which will be 2. We're going to multiply that leading coefficient by the x value and write the product up under the second coefficient. Then you're going to add vertically, so negative 5 plus 6 is 1. Now we're going to go back and multiply 1 times 3 and put it under our next coefficient, and then add vertically. So 0 plus 3 is 3. Then we multiply again, 3 times 3 is 9, and then we add vertically, which is 5. And then finally, 5 times 3 is 15, and we add vertically. So the final sum is the value of that, the last value. We call that our remainder, but that means when we plug in 3, we will get 23. Let's try this polynomial. So let's find g of 4 for this using synthetic substitution. So let's pull off those coefficients and write them in our space. So 1, negative 5, 6, and 1. Use our elongated L just as an organizer, and then put 4 out to the side. So start by bringing down your leading coefficient of 1. You're going to multiply and add vertically, and then multiply, so negative 4, and add vertically, and now multiply diagonally, so 4 times 2 is 8, and then add. So g of 4 equals 9. Once you get the hang of this method, sometimes it just is really convenient to do rather than directly plugging in. Let's do some more practice. So let's classify, these equations, see if they're polynomials. So let's go back to the criteria and look at the exponents. 3, 4, and 1, all whole numbers, and we have all real number coefficients. So yes, this is a polynomial. It's not in standard form though, so let's rewrite it and put our biggest exponent term first. And then just work our way down. So 2/3 x cubed, and then minus 12x. So its degree is that biggest exponent, so 4, and that's a quartic. And then our leading coefficient is the number in front of our x to the 4th, so square root of 5. Now number 2, let's start again. Is it a polynomial? Well, we'll see. We'll evaluate those exponents. But then right away I see I have an imaginary leading coefficient there. And so that is not a polynomial. It's an equation, but not one that we're going to work with in this unit. All right, let's evaluate this using direct substitution. So I'm plugging in negative 6 into my g function. So negative 6 goes in. I recommend plugging it in when you write it down using parentheses. When you put it in your calculator, also use parentheses so that your calculator will raise the negative to the powers that it needs to. So we'll get 6,480 plus 432 minus 54 minus 10, which will give us 6,848. Now let's do the same thing with synthetic substitution. Notice we're missing an x squared term, so we need to put a 0 in, and then we put our negative 6 out to the side. So we bring down our leading coefficient, we multiply and then add, multiply and add, multiply and add diagonally, and then multiply and finally add diagonally, and see that we get the same results. So g of negative 6 equals 6,848. All right, example 5, a real life situation. So the weight of an ideal round cut diamond can be modeled by this equation, where weight is the weight of the diamond in carats, or W, and then D is the diameter in millimeters. So according to the model, this equation, what is the weight of a diamond with a diameter of 12 millimeters? Well, I'm just going to use direct substitution rather than synthetic substitution, and I'm plugging in 12 for diameter. I just need to remember to put my exponents where I need to. And then I'm going to carefully plug that into my calculator just as you see it there. I'm going to round to tenths place. So this would be, yikes, a big diamond, 8.5 carats. All right, this concludes our notes on classifying and evaluating polynomials, concept 13.